This includes polynomials with real coefficients, since every real number is a complex number with an imaginary part equal to 0. Equivalently, the theorem states that the field of complex numbers is algebraically closed. The theorem is also stated as follows. Every non-zero, single-variable, degree n polynomial with complex coefficients has, counted with multiplicity, exactly n roots. The equivalence of the two statements can be proven through the use of successive polynomial division. In spite of its name, there is no purely algebraic proof of the theorem, since any proof must use the completeness of the rails, which is not an algebraic concept. Additionally, it is not fundamental for modern algebra. Its name was given at a time when the study of algebra was mainly concerned with the solutions of polynomial equations with real or complex coefficients. History. Peter Roth, in his book Arithmetica Philosophica, wrote that a polynomial equation of degree n may have n solutions. Albert Girard, in his book L'Invention nouvelle en l'algèbre, asserted that a polynomial equation of degree n has n solutions, but he did not state that they had to be real numbers. Furthermore, he added that his assertion holds, unless the equation is incomplete, by which he meant that no coefficient is equal to 0. However, when he explains in detail what he means, it is clear that he actually believes that his assertion is always true. For instance, he shows that the equation x4 equals 4x minus 3, although incomplete, has four solutions. 1 minus 1 plus I square root 2, and minus 1 minus I square root 2, as will be mentioned again below. It follows from the fundamental theorem of algebra that every non-constant polynomial with real coefficients can be written as a product of polynomials with real coefficients whose degree is either 1 or 2. However, in 1702 Leibniz said that no polynomial of the type x4 plus a4 can be written in such a way. Later, Nicolaus Bernoulli made the same assertion concerning the polynomial x4 minus 4 by 3 plus 2 by 2 plus 4x plus 4. But he got a letter from Euler in 1742 in which he was told that his polynomial happened to be equal to where alpha is the square root of 4 plus 2 square root 7. Also, Euler mentioned that a first attempt at proving the theorem was made by D'Alembert in 1746, but his proof was incomplete. Among other problems, it assumed implicitly a theorem which would not be proved until more than a century later, and furthermore the proof assumed the fundamental theorem of algebra. Other attempts were made by Euler, de Fontenay, Lagrange, and Laplace. These last four attempts assumed implicitly Girard's assertion. To be more precise, the existence of solutions was assumed, and all that remained to be proved was that their form was a plus bi for some real numbers a and b. In modern terms, Euler, de Fontenay, Lagrange, and Laplace were assuming the existence of a splitting field of the polynomial p. At the end of the 18th century, two new proofs were published which did not assume the existence of roots. One of them, due to James Wood and mainly algebraic, was published in 1798 and it was totally ignored. Wood's proof had an algebraic gap. The other one was published by Gauss in 1799 and it was mainly geometric, but it had a topological gap, filled by Alexander Ostrovsky in 1920. As discussed in Smale 1981. A rigorous proof was published by Argand in 1806. It was here that, for the first time, the fundamental theorem of algebra was stated for polynomials with complex coefficients, rather than just real coefficients. Gauss produced two other proofs in 1816 and another version of his original proof in 1849. The first textbook containing a proof of the theorem was Corky's Cours d'analyse de l'École Royale Polytechnique. It contained Argand's proof, although Argand is not credited for it. None of the proofs mentioned so far is constructive. It was Weierstrass who raised for the first time, in the middle of the 19th century, the problem of finding a constructive proof of the fundamental theorem of algebra. He presented his solution, that amounts in modern terms to a combination of the Durand-Kerner method with the homotopy continuation principle. In 1891, another proof of this kind was obtained by Helmuth Kneser in 1940 and simplified by his son Martin Kneser in 1981. Without using countable choice, it is not possible to constructively prove the fundamental theorem of algebra for complex numbers based on the Dedekind real numbers. However, Fred Richman proved a reformulated version of the theorem that does work. Proofs. All proofs below involve some analysis, or at least the topological concept of continuity of real or complex functions. Some also use differentiable or even analytic functions. This fact has led to the remark that the fundamental theorem of algebra is neither fundamental, nor a theorem of algebra. Some proofs of the theorem only prove that any non-constant polynomial with real coefficients has some complex root. This is enough to establish the theorem in the general case because, given a non-constant polynomial p with complex coefficients, the polynomial has only real coefficients, and if z is a zero of q, then either z or its conjugate is a root of p. A large number of non-algebraic proofs of the theorem use the fact that an nth degree polynomial function p whose dominant coefficient is 1 behaves like zinc when z is large enough. A more precise statement is, there is some positive real number r such that, when z greater than r, complex analytic proofs find a closed disk d of radius r centered at the origin such that p greater than p whenever z r. The minimum of p on d, which must exist since d is compact, is therefore achieved at some point z0 in the interior of d, but not at any point of its boundary. The maximum modulus principle implies then that p equals 0. In other words, z0 is a zero of p. A variation of this proof does not require the use of the maximum modulus principle. If we assume by contradiction that a equals p0, then, expanding p in powers of z minus z0, we can write here, the Cj is simply the coefficients of the polynomial zp, and we let k be the index of the first coefficient following the constant term that is non-zero. But now we see that for z sufficiently close to z0 this has behavior asymptotically similar to the simpler polynomial, in the sense that the function is bounded by some positive constant m in some neighborhood of z0. Therefore, if we define and let then for any sufficiently small positive number r, using the triangle inequality, we see that when r is sufficiently close to 0 this upper bound for p is strictly smaller than a, in contradiction to the definition of z0, smaller in absolute value than p. Another analytic proof can be obtained along this line of thought, observing that, since p greater than p outside d, the minimum of p on the whole complex plane is achieved at z0. If p greater than 0, then 1, p is a bounded holomorphic function in the entire complex plane, since, for each complex number z, 1 p, applying Liouville's theorem, which states that a bounded entire function must be constant. This would imply that 1 p is constant and therefore that p is constant. This gives a contradiction, and hence p equals 0. Yet another analytic proof uses the argument principle. Let r be a positive real number large enough so that every root of p has absolute value smaller than r. Such a number must exist because every non-constant polynomial function of degree n has at most n zeros. For each r greater than r, consider the number where C is the circle centered at 0 with radius r oriented counterclockwise. Then the argument principle says that this number is the number n of zeros of p in the open ball centered at 0 with radius r, which, since r greater than r, is the total number of zeros of p. On the other hand, the integral of n, z along C divided by 2 pi I is equal to n. but the difference between the two numbers is the numerator of the rational expression being integrated has degree at most n1 and the degree of the denominator is n plus 1. Therefore, the number above tends to 0 as r plus infinity, but the number is also equal to n minus n and so n equals n. Still another complex analytic proof can be given by combining linear algebra with the Cauchy theorem, to establish that every complex polynomial of degree n greater than 0 has a 0. It suffices to show that every complex square matrix of size n greater than 0 has a eigenvalue. The proof of the latter statement is by contradiction. Let A be a complex square matrix of size n greater than 0 and let n be the unit matrix of the same size. Assume A has no eigenvalues. Consider the resolvent function, which is a meromorphic function on the complex plane with values in the vector space of matrices. The eigenvalues of A are precisely the poles of R. Since, by assumption, A has no eigenvalues, the function R is an entire function, and Cauchy theorem implies that on the other hand, R expanded as a geometric series gives. This formula is valid outside the closed disk of radius A. Let R greater than A. Then, this is a contradiction, and so A has an eigenvalue. Finally, Rutsch's theorem gives perhaps the shortest proof of the theorem. Topological proofs let Z0C be such that the minimum of P on the whole complex plane is achieved at Z0. It was seen at the proof which uses Leopold's theorem that such a number must exist. We can write P as a polynomial in Z minus Z0. There is some natural number k and there are some complex numbers ck plus 1, cn such that ck 0 and that in the case that P is non-zero. It follows that if A is a kth root of minus P, ck and if T is positive and sufficiently small, then P less than P, which is impossible, since P is the minimum of P on D. For another topological proof by contradiction, suppose that P has no zeros. Choose a large positive number R such that, for Z equals R, the leading term zinc of P dominates all other terms combined, in other words, such that Z n greater than and minus 1 zinc minus 1 plus A 0. As Z traverses the circle given by the equation, Z equals R once counterclockwise, P, like zinc, winds n times counterclockwise around 0. At the other extreme, with Z equals 0, the curve P is simply the single point P, whose winding number is clearly 0. If the loop followed by Z is continuously deformed between these extremes, the path of P also deforms continuously. We can explicitly write such a deformation as A equals pi theta, where 0 t1. If one views the variable t as time, then at time 0 the curve is P and at time 1 the curve is P. Clearly at every point t, P cannot be 0 by the original assumption, therefore during the deformation, the curve never crosses 0. Therefore the winding number of the curve around 0 should never change. However, given that the winding number started as n and ended as 0, this is absurd. Therefore, P has at least one 0. Algebraic proofs. These proofs use two facts about real numbers that require only a small amount of analysis. Every polynomial with odd degree and real coefficients has some real root. Every non-negative real number has a square root. The second fact, together with the quadratic formula, implies the theorem for real quadratic polynomials. In other words, algebraic proofs of the fundamental theorem actually show that if R is any real closed field, then its extension C equals R is algebraically closed. As mentioned above, it suffices to check the statement, every non-constant polynomial P with real coefficients has a complex root. This statement can be proved by induction on the greatest non-negative integer k such that 2k divides the degree n of P. Let A be the coefficient of sinc in P and let F be a splitting field of P over C. In other words, the field F contains C and there are elements Z1, Z2, zinc in F such that if K equals 0, then N is odd, and therefore P has a real root. Now, suppose that N equals 2 kilometers and that the theorem is already proved when the degree of the polynomial has the form 2k minus 1 meter, with M odd. For a real number t, define, then the coefficients of quarter-symmetric polynomials in the Z's with real coefficients. Therefore, they can be expressed as polynomials with real coefficients in the elementary symmetric polynomials, that is, in -a1, a2, nan. So quart has in fact real coefficients. Furthermore, the degree of quart is n, 2 equals 2k minus 1 meter, and m is an odd number. So, using the induction hypothesis, quart has at least one complex root. In other words, z plus zj plus zz is complex for two distinct elements I and j from 1, n. So, both z plus zj and zz are complex numbers. It is easy to check that every complex number has a complex square root. Thus every complex polynomial of degree 2 has a complex root by the quadratic formula. It follows that z and zj are complex numbers, since they are roots of the quadratic polynomial z2 minus z plus zz. J. Shipman showed in 2007 that the assumption that odd-degree polynomials have roots is stronger than necessary. Any field in which polynomials of prime degree have roots is algebraically closed. For axiomatization of algebraically closed fields, this is the best possible, as there are counterexamples if a single prime is excluded. However, these counterexamples rely on -1 having a square root. If we take a field where -1 has no square root, and every polynomial of degree ni has a root, where I is any fixed infinite set of odd numbers, then every polynomial f of odd degree has a root. Kf has a root, where k is chosen so that dag plus 2ki. Another algebraic proof of the fundamental theorem can be given using Galois theory. It suffices to show that C has no proper finite field extension. Let K, C be a finite extension. Since the normal closure of K over R still has a finite degree over C, we may assume without loss of generality that K is a normal extension of R. Let G be the Galois group of this extension, and let H be a Solow-2 subgroup of G, so that the order of H is a power of 2, and the index of H in G is odd. By the fundamental theorem of Galois theory, there exists a sub-extension L of K, R such that Gal equals H, as L, R, equals G, H, is odd, and there are no nonlinear irreducible real polynomials of odd degree. We must have L equals R. Thus K, R, and K, C are powers of 2. Assuming by way of contradiction that K, C greater than 1, we conclude that the 2 group Gal contains a subgroup of index 2. So there exists a sub-extension M of C of degree 2. However, C has no extension of degree 2, because every quadratic complex polynomial has a complex root, as mentioned above. This shows that K, C equals 1, and therefore K equals C, which completes the proof. Geometric proofs. There exists still another way to approach the fundamental theorem of algebra, due to J. M. Almira and A. Romero, by Riemannian geometric arguments. The main idea here is to prove that the existence of a non-constant polynomial p without zeros implies the existence of a flat Riemannian metric over the sphere S2. This leads to a contradiction, since the sphere is not flat. Recall that a Riemannian surface is said to be flat if its Gaussian curvature, which we denote by kilogram, is identically null. Now, Gauss-Bonnet theorem, when applied to the sphere S2, claims that, which proves that the sphere is not flat. Let us now assume that n greater than 0 and p equals a0 plus a1z plus a n z n 0 for each complex number z. Let us define p asterisk equals z n p equals a0 zinc plus a1 zinc minus 1 plus n. Obviously, p asterisk 0 for all z in C. Consider the polynomial f equals p asterisk. Then f0 for each z in C. Furthermore, we can use this functional equation to prove that g, given by for w in C, and for ws2, 0, is a well-defined Riemannian metric over the sphere S2. Now, a simple computation shows that, since the real part of an analytic function is harmonic, this proves that kilogram equals 0. Corollaries. Since the fundamental theorem of algebra can be seen as the statement that the field of complex numbers is algebraically closed, it follows that any theorem concerning algebraically closed fields applies to the field of complex numbers. Here are a few more consequences of the theorem, which are either about the field of real numbers or about the relationship between the field of real numbers and the field of complex numbers. The field of complex numbers is the algebraic closure of the field of real numbers. Every polynomial in one variable z with complex coefficients is the product of a complex constant and polynomials of the form z plus a with a complex. Every polynomial in one variable x with real coefficients can be uniquely written as the product of a constant. Polynomials of the form x plus a with a real, and polynomials of the form x2 plus x plus b with a and b real and a2 minus 4b less than 0. This implies that the number of non-real complex roots is always even. Every rational function in one variable x, with real coefficients, can be written as the sum of a polynomial function with rational functions of the form a, n, and rational functions of the form n. A corollary of this is that every rational function in one variable and real coefficients has an elementary primitive. Every algebraic extension of the real field is isomorphic either to the real field or to the complex field.